This week, we will be working on Lab 10, Torques and Rotational Equilibrium. In this video, I will give you a brief introduction to the theory and to the simulator. So as you might know, there are two conditions that an object should be satisfied for that object to be in mechanical equilibrium. The first condition is the net external force acts on that object should adds up to 0. So summation of forces should be 0. So if you apply F equal ma, the Newton's second law, as the net force is 0, the acceleration should be 0. So in this case, when the net force is 0, there's no translational acceleration. So the object is in translational equilibrium. Then the second condition is the net external torque should adds up to 0. So when you adds up the torques acting on an object, it should adds up to 0. In this case, we can apply tau equal I alpha, which you have learned in the last week lab. So in this case, if the net torque is 0, then the alpha or the rotational acceleration will be 0. So when an object satisfies these both conditions, then the object will be in translational equilibrium and the rotational equilibrium. In this case, we will be saying that the object is in mechanical equilibrium. Now, here's an example of a natural object that is in a mechanical equilibrium. So this is a picture of a large balanced rock at the Garden of Gods in Colorado. So this, as you see here, this big rock is attached to the ground by this area, right? But the rock is really huge. You can compare with the size of the person standing up here. However, this big rock is in mechanical equilibrium. It is not rotating or rolling over this edge, or it is not linearly moving at all. Now, so when we go apply some mathematics into this concept, let's think about there's a force acting on a hinge point, like it's hinged at the center, and let's say we are applying a force over here. So maybe you can imagine about a rolling door, right? So this door is eligible to go all the way around this hinge point, right? So let's say we apply a force along this way, and let's say there's it's when we apply this force that let the door to open in this direction, so in the counterclockwise direction. So the equation for torque is force cross product with the length. So in symbols, we may write it as torque equal R cross F. And here F is the force, R means the distance from the hinge point to the location where we are applying the force. Now we can simplify this cross product as RF sine theta, where the theta being the angle between R and F. So here you see these symbols, right? So the torque is a vector. So there should be a direction that involved with the torque. So we should be able to find the direction of torques, right? So in this case, we can use the right hand rule. So what we're going to do is we are using our right hand, extend your 4 fingers and point it in the direction of force. Point the yeah, you may do the other way around as well. So you take your 4 fingers and point it along the direction of the position vector. So you basically keep your 4 fingers in this direction from the hinge point towards where it's applying force. Then you curl your 4 fingers towards the applied force. Then your thumb is pointing in the direction of the torque. Now let's try that right hand rule in this scenario. So force is applying upward like this one on the figure here, and the R direction the R can be measured from the hinge point towards the force. So you keep your 4 fingers along this way. Remember, it is right hand, right? So you use your right hand, keep your 4 fingers towards this way, so towards force, and then you curl your 4 fingers in the direction of force. So what do you see? Is your thumb directing like it's coming out from the screen towards you? Then it's correct. If not, please try it again. Use your right hand, keep your 4 fingers towards the force, and then curl your 4 fingers towards the applied force direction, then your thumb should be directing towards the torque direction. Now you might say the torque direction is counterclockwise. It's okay, we can accept that as long as you're consistent with the direction that you're watching the scenario, and also if you're consistent with your full work. So in the lab, you may use right hand rule to find the direction, or you may take clockwise and counterclockwise notations as the directions that you define. Well, so in the lab, basically we are using the idea of teeter-totter setup, right? So teeter-totter, maybe you remember, like when you were kids, you were used to play in these teeter-totters, right? So if the teeter-totter is in mechanical equilibrium, then there are two conditions that to satisfy. The net external forces should be 0, and the net external torque should be 0 as well, right? So when you're talking about external forces in this setup, let's forget about frictions for our easiness. So that is our assumption. So let's assume that this is a physics setup, no friction at all. Then the forces acting on the objects should be the weight of the girl, the weight of the man, and then the weight of this seat, the rod or the seat, and then the force that created by the hinge point upward, balancing out all these forces, right? So this normal force acts from the hinge towards upward should balance with the weight of the girl, weight of the boy, and the weight of the seat, right? Then the net external torque should be 0. So you're taking the torque around the hinge point. So when you're talking the torque around this point, then the normal force and the weight of the rod is acts at that point. So there's no torque contribution from the normal force or the weight of the seat, but the man and the girl are creating torques around the hinge point because their weight is displaced from the hinge point. So this person is weight is acting downward. So it's make the teeter-totter rotates in the clockwise direction, right? So it is clockwise direction. Now you may use your right hand to find the torque direction. So the R along this way towards right, and the force act downward. So if you use your right hand and keep the 4 fingers towards the person from the hinge point, and then you curve your 4 fingers in the direction of force, so downward direction. So your thumb is pointing into the screen, right? So it is the torque is into the screen by the man. Likewise, if you try the same right hand rule to the girl, so your right hand, your 4 fingers are pointing towards the girl from the hinge point, then you curve it towards down, then your thumb is pointing away from the screen, right? So the two torques that acts by the person and the girl acts in the 2 different directions. So likewise, you may define your torque directions when you're working on the lab manual or the lab report. But still you may use the words counterclockwise and clockwise directions, or you may define the man is creating a clockwise direction and rotation, and that is a positive rotation, or this one, the girl is creating a negative rotation. So likewise, you may consistent with your definition of directions of torques. Well, here, this is for you to enjoy. So, hey, Anna Mary, you want to see how gravity works? So you can imagine what would happen, right? So that's just for the fun. So when you have a time, just think about it. Or maybe you can start creating your own cartoons. Well, so let me share the simulator with you, and I'll show you like how the simulator worked for us this time. So when you open the simulator, it should look like this one, where you have access to the intro of the balancing act experiment or the balancing lab and the game. Game is for your fun. So if you have time, you may go over there and play a couple of games about torque, and it is really cool. But in the real lab, we are using balancing lab. So click on that. It will open to your screen like this, where you can mark the level. So that's indicate where the level location is. And also you can click the force from the objects if you like. It's not necessary, but you may use that as an option. Also, you need to use the ruler. So in that case, you may read the location of masses. And then you may place the masses. You may grab masses from this side and you can place it somewhere that you want. You can add bunch of masses, right? You can even move it, and if you want to put it back, you just move it back to the menu over here. And then to check whether it is balanced, you have to switch on the simulator. See, it is not balanced, but you can move these masses and see where, if there's a location that it can balance out, right? So in this case, it's about to balance. Yes, it's balanced. So you, as you see, this teeter-totter balancing out. So you see, like, it's with the markers, you may read these markers, you can read the level position. So that way you can make sure that it is balanced. So in the experiment, what you're going to do is you're going to grab some directed masses and keep it as it's directed, and then you're going to balance the other side to see which location does the teeter-totter get balanced. All right, so thank you, and I hope this will help you to complete the lab report successfully. So the lab manual is available as a PDF and also as a Word document. So please be mindful when you are writing your lab report, make it really nicely formatted so it's easy for our grader TA to grade. And this is the last lab for the spring 2020. So it's really nice that you completed half of the Physics 207 labs in a real lab setting and half online. So congratulations, and hopefully I'll see you in the fall semester on campus.